Every time a nurse looks at an ECG monitor, to save a patient from cardiac arrest, they're actually using this 400-year-old math trick.
Right,
Yeah.
yeah. A trick that was originally designed to bridge the massive gap between physical shapes and abstract numbers.
It's crazy because it's totally hiding in plain sight.
Oh, absolutely. We look at a blank piece of graph paper, and I mean, it just looks like a bunch of empty little boxes,
Right.
very static.
Yeah.
But the moment you connect that grid to real-world data, those intersecting lines start telling a high-stakes story right in real time.
Welcome to this deep dive. Today, we have a really specific mission.
Mm-hmm.
For those of you out there gearing up for the TEAS and HESI nursing entrance exams, consider this your ultimate prep session. We are taking on the coordinate plane.
Which is such a massive topic.
It really is. And our goal today isn't just to, help you memorize a bunch of formulas so you can pass a test. We're looking at a stack of sources that cover the definitions, the surprisingly messy history, the strict rules, and the real-world clinical applications of reading and plotting on the XY grid.
Right.
We want you to understand exactly why this system exists and how it actively saves lives in healthcare.
Because, while this concept, plotting an X and a Y, is something we routinely teach to 10-year-olds today, if we step back, it's arguably one of the most powerful intellectual breakthroughs in human history.
That's a big claim.
I mean it, though. It fundamentally changed how we monitor our environment and eventually the human body.
Well, before we get into the exam mechanics, we should probably define what this thing actually is.
Good idea.
When you open a test booklet and see that grid, what are the core components?
So in modern terms, the coordinate plane, which, you'll also hear called the Cartesian plane or the rectangular coordinate system, is a two-dimensional surface. It's formed by two perpendicular number lines. You have a horizontal line, which is the x-axis, and then you have a vertical line, which is the y-axis.
Right, and they cross right in the middle.
Exactly. They cross at exactly one reference point called the origin, where both values are 0.
And every point on that grid gets a unique address, right? The ordered pair.
Correct. Every single location on this plane corresponds to exactly one ordered pair of numbers. It's written as X, Y, usually in parentheses.
I noticed the sources place a massive emphasis on that word ordered.
Oh, it is the absolute foundation of the system. The X always tells you how far to move horizontally from the origin, and the Y always tells you how far to move vertically.
So they aren't interchangeable.
Not at all. If you have the pair 3, 5, you are in a completely different physical location than if you plotted 5, 3.
Right. To really understand why this is so revolutionary, I kind of want to bring up an analogy.
Let's hear it.
I like to think of this system like a smartphone translation app. Imagine geometry is one language. It's all about, physical maps, pictures, distances, triangles, and circles. Then you have algebra, which is a completely different language. It's all abstract equations, ordered pairs, and pure numbers.
Right, what mathematicians call R squared. Pure algebraic structure with no inherent visual picture attached to it.
Exactly. And for centuries, these two languages couldn't talk to each other. You couldn't easily turn a physical shape into an equation.
No, you couldn't.
So the coordinate plane is the bridge. It's the translation app that lets you convert freely between a physical shape and a mathematical equation. Here's where it gets really interesting, at least for test takers.
No, definitely.
The sources note this as misconception number 5. A lot of students treat graphing and solving equations as two completely different topics on the TEAS or HESI.
Right, they memorize one set of rules for the algebra section and another set for the graphing section.
Which just doubles the amount of work you have to do.
It does, and it misses the whole point. A graph is literally just a picture of an equation. And an equation is just the algebraic description of a graph.
So they're the exact same thing.
Exactly. If you solve an equation for y and get a set of numbers, those numbers are just the physical dots on your grid, just translated into a different language.
Wait, hold on, though. You're kind of ruining my childhood here with this whole translation thing.
Uh-oh. Why is that?
Because I specifically remember my middle school math teacher telling me that René Descartes invented this whole translation system in one sudden flash of brilliance.
Oh, let me guess. The fly on the ceiling.
Yes. The story goes that he was sick in bed, staring at his ceiling, and he watched a fly land. And he realized he could pinpoint the exact location of that fly by measuring its distance from two intersecting walls in the corner of his room.
Right.
So, are you telling me the fly story is fake?
I am so sorry, but yes, it is a very popular but entirely busted myth.
Wow, really?
Yeah, historians have scoured Descartes' writings and contemporary accounts from the 17th century, and that fly story appears absolutely nowhere.
That is wild.
Okay.
It is taught as historical fact everywhere. So how did it actually happen?
Well, what's fascinating here is that it was a very messy evolution. The modern, perfectly symmetrical grid with a clean crosshair in the middle that we use today, that was not a single flash of insight.
It wasn't.
No, the original inventors in the 17th century didn't even use two cross axes. They usually just drew a single reference line, like a horizontal axis, and then measured a second quantity as a vertical length coming off of that line.
Oh, interesting.
And they almost exclusively worked in positive numbers.
So no negative numbers stretching off into infinity.
No, not at first. The fully symmetric four-quadrant system with negative numbers took about 150 years of incremental cleanup by later mathematicians to fully standardize.
150 years.
Yeah. Descartes published the core idea in 1637 in an appendix called La Géométrie. His Latinized name is Cartesius, which is, why we call it the Cartesian plane. Ah, that makes sense.
But even his own diagrams look absolutely nothing like modern graph paper.
And the plot thickens, because the sources point out Descartes wasn't even the only one working on this, right?
He arguably wasn't even the first. There was a French lawyer and mathematician named Pierre de Fermat.
Okay.
He developed a strikingly similar system of relating equations to curves between 1629 and 1636, which actually predates Descartes' publication.
Oh, wow.
But Fermat only circulated his work privately in manuscripts among friends. It wasn't printed until 1679, which was long after his death.
Ah, a classic case of publish or perish. It's all about who gets to the printing press first.
Exactly. Publication timing often dictates historical memory. And I mean, if we look even further back, there's a medieval predecessor named Nicole Oresme in the 14th century.
So roughly 250 years earlier.
Right. Fermat developed a technique for plotting the intensity of varying qualities, like heat or velocity against time. And he used perpendicular reference lines to do it.
So he basically invented the line graph in the 1300s. Essentially, yeah. It wasn't strictly algebraic, so we consider it a conceptual ancestor, but it proves the underlying idea of using two perpendicular measurements to track a changing quantity was floating around long before the 17th century.
Regardless of who gets the historical credit, though, if you are sitting down for a nursing entrance exam, you don't need the historical drama.
No, definitely not.
You need the mechanics.
Yeah.
So let's pivot to what this actually looks like on test day, because the rules are beautifully strict.
They really are. Strip away the history, and it all rests on first principles.
Yeah.
If you follow the mechanical rules, you will get the correct answer every single time.
Okay, let's go over the golden rules. Rule 1, two number lines. The x-axis goes horizontally. Positive numbers take you to the right of the origin. Negative numbers take you to the left. And then the y-axis goes vertically. Positive takes you up, negative takes you down.
And rule 2 brings us back to those ordered pairs. To plot x, comma, y, you always move horizontally first, then vertically.
I used to use the old walk down the hallway before you take the elevator trick to remember this.
That's a classic one.
But for adults heading into healthcare, there's a much better clinical mnemonic.
Oh, let's hear it.
Think of X as walking horizontally across the hospital ward to find the right patient's room.
Okay, I like that.
Once you are standing at the bed, Y is adjusting the bed up or down vertically. You can't adjust the bed until you've walked to the right room. Room first, bed second.
Yeah.
X first, Y second.
That visual works perfectly. So if a test asks you to plot -3, 4, you start at the origin.
Yeah.
You walk across the ward 3 units to the left because x is -3. Then you raise the bed up 4 units because y is +4.
And when you finish that movement, you are standing in a specific quadrant. The TEAS and HESI A2 exams love to test quadrant identification.
They really do.
The plane is divided into 4 sections, and they run counterclockwise, starting from the upper right. Can you walk us through the signs for each one?
Absolutely. Quadrant I is the upper right. Both your x and y movements were in the positive direction, so the coordinates are always positive, positive.
Okay.
Quadrant 2 is the upper left. You moved left, so x is negative, but you moved up, so y is positive, negative, positive.
Got it.
Quadrant 3 is the lower left. You moved left and down. Both coordinates are negative.
And finally, quadrant 4.
Right. Quadrant 4 is the lower right. You moved right, which is a positive x, and down, which is a negative y, positive, negative.
So going back to our point, -3, 4. Left 3, up 4. We landed in quadrant 2.
Exactly. But this raises an important question, and it's one that trips up a lot of students mechanically.
What's that?
What happens if a point lands exactly on one of the lines? Let's say the point 0, comma, -5.
Oh, that's a good one.
You didn't move left or right across the ward at all. Your x is 0. You just lowered the bed 5 units. What quadrant are you in?
According to the sources, you are in no quadrant.
Right.
If a point has a 0 for either the x or the y coordinate, it sits directly on an axis. It technically does not belong to any of the 4 quadrants, and exams will totally try to trick you with that.
They absolutely will. They'll give you 0, 4 and ask if it's in quadrant I or quadrant 2. The answer is neither. It's just sitting on the fence.
We should probably also clear up a few other common misconceptions that plague test takers.
Yeah, let's do it. Misconception 3 in the sources is the belief that the origin, 0, 0, always has to be placed in the bottom left corner of your graph paper.
Oh man, I used to do this all the time. We naturally want to deal with positive numbers, right? So we cram the axis down into the corner, so we only have to look at quadrant 1.
It's a very common habit. But the origin is simply wherever the 2 axes cross. It can be right in the middle of your page. Conceptually, the plane extends infinitely in all 4 directions.
What about plotting numbers that aren't whole integers? Misconception 4 is thinking off-grid points can't be plotted.
Right, like if an exam gives you 2.5, comma, -1.75.
Yeah, it feels wrong because it doesn't land on a neat little crosshair.
I know the feeling, but coordinates are just real numbers. They can be decimals, fractions, or even irrational numbers like pi. They live in the infinite spaces between the grid lines. The mechanics of finding them are exactly the same.
This brings up a really important question for the listener. Why does nursing care about this so much?
A very fair question.
Because you are not going to be sitting in an intensive care unit with a number 2 pencil plotting decimals on graph paper.
Right, you won't be drawing grids, but you will be interpreting them constantly. The Cartesian plane is the literal foundation of how clinical data is visualized in medicine.
Think back to our opening example of an ECG, an electrocardiogram.
Exactly. The squiggly lines monitoring a heartbeat on the monitor. That monitor is fundamentally a Cartesian coordinate plot.
Oh, really?
Yeah, the horizontal x-axis represents time, usually in milliseconds, and the vertical y-axis represents electrical voltage from the heart muscle.
So when a healthy heart beats, it creates that very specific algebraic wave, the PQRST complex.
Yes. And when a nurse looks at an ECG and identifies a dangerous arrhythmia like ventricular tachycardia, what they are actually doing is looking at a geometric curve and recognizing that its shape deviates from the normal algebraic pattern.
Right.
A dropped beat is just a Y value of 0 where there should have been a voltage spike.
So reading a heart rhythm is really just translating algebra into a patient's physical status.
Exactly.
What about something more long-term, like in pediatrics?
Pediatric growth charts are a perfect example of scatter plots and trend lines. The x-axis is the child's age in months or years. The y-axis is their weight or height.
Right.
Over multiple visits, clinicians plot those ordered pairs. When you connect those dots, you form a line. If a child's line suddenly drops from the 80th percentile curve down to the 40th percentile curve, that change in the line's slope immediately signals a potential developmental or nutritional issue.
You've also seen this heavily in public health with epidemic curves.
Right. Oh, everywhere. You have dates on the x-axis and the number of positive cases on the axis. By reading the steepness of that curve, officials can instantly visualize whether an outbreak is spiking out of control or fading out.
It's everywhere, even outside of medicine.
Oh, yeah. Every time you open a rideshare app or use GPS on your phone, latitude and longitude function exactly like a Y value and an X value on a global grid.
Right. The software calculates your coordinates and translates that algebra to drop a physical pin on your screen.
Precisely.
So a future nurse isn't really learning grid paper. They are learning the foundational language of vital sign trends and pharmacology dosage graphs. Descartes handed us the ability to translate unseen variables into visual patterns so we can actually interpret what's happening inside the human body.
And if we connect this to the bigger picture, because this tool is so heavily relied upon, misusing it can have catastrophic consequences.
How so?
Well, if you misinterpret a scale or flip an X and a Y, your understanding of the data is entirely backward.
It's interesting you mention that because historical mathematicians actually fought against parts of this system. In the 17th and 18th centuries, many prominent thinkers fiercely debated the legitimacy of negative coordinates.
They really did. They were deeply uncomfortable with the idea of a negative length.
Why?
They argued, how can a point exist in a direction that has no physical counterpart? You can't have a negative apple, so how can you have a negative position?
That's a fair point for back then.
It took decades for negative values on the X and Y axis to be fully accepted as standard practice.
Which perfectly ties into misconception 2 from our sources. A lot of students get a negative number in their calculation and panic, assuming they made a mistake.
Right, but negative numbers are perfectly valid positions. Quadrants 2, 3, and 4 are built entirely out of negative coordinates. They simply represent a position to the left of the origin or below it.
If you flip an X and a Y on a patient's chart, a dosage could be administered backward over time. And the consequences of a mismatched grid aren't just limited to healthcare either.
No, definitely not.
There was a massive disaster at NASA in the late 90s caused by a coordinate failure, right?
Yes, the Mars Climate Orbiter in 1999. NASA literally lost a multi-million-dollar spacecraft because of a unit mismatch on their grids.
Oh man, that's rough.
One engineering team programmed their software using metric units, newtons, for a navigation calculation. The other team's software used imperial units, pound force.
So they were basically speaking 2 different languages on the same grid.
Exactly. The numbers were plotted, but the scales represented entirely different physical realities. The spacecraft approached Mars on the wrong trajectory and just burned up in the atmosphere.
That is brutal.
No.
But the lesson for students is crystal clear. Pay attention to your axis labels and units.
Always.
If you mismatch your scales, your graph is going to be wildly numerically wrong, even if the dots look pretty on the page. Your personal Mars orbiter will burn up on test day.
And, as you prepare for test day, you'll see this Cartesian plane is the foundation for a whole neighborhood of other terms on the exam. It's worth explaining how these concepts actually operate on the grid, because you really can't solve them without it.
Let's do a quick lightning round. Walk us through them. Slope is a huge one. Rise over run.
Right. Slope is just a measure of how steep a line is. You pick 2 points on a line, and you calculate how much the I value changes, which is the rise, compared to how much the X value changes the run.
And in a clinical setting.
In a clinical setting, slope might represent how fast a medication concentration is dropping in a patient's bloodstream over time.
Okay, next. Linear equations.
Yeah.
Usually written as y equals mx plus b.
That equation is just the DNA of a straight line. The m represents that slope we just talked about, and the b is the y-intercept.
The exact spot where the line crashes through the y-axis.
Exactly. If you know those 2 things, you can draw the entire infinite line.
We mentioned scatter plots earlier with pediatric charts. The sources say these are heavily tested on the science sections.
Yep. A scatter plot is what happens when you plot a bunch of real-world data points to see if they're related.
Like trying to find a correlation.
Right. If you plot a patient's daily sodium intake on the x-axis and their blood pressure on the y-axis, and all the dots clump together in a pattern that slopes upward to the right, you can visually see a positive correlation. As sodium goes up, blood pressure goes up.
Got it. The sources also mention distance and midpoint formulas.
Which are simply algebraic tools. The distance formula uses the Pythagorean theorem to tell you exactly how far apart 2 points are on the grid.
Have the midpoint.
The midpoint formula just averages the x-coordinates and the y-coordinates to find the exact halfway mark between them.
Okay, last one. Functions. The exams love asking if a graph represents a function.
Oh, they do. A function is a strict rule. For every x value, there can only be one I value. To prove it visually on the coordinate plane, you use the vertical line test.
How does that work?
If you can draw a perfectly vertical line anywhere on the graph and it hits the curve more than once, it is not a function.
Oh, I see.
Think about a patient's temperature. At exactly 2:00 p.m., which is your x value, the patient can only have one temperature, your A value.
Right. They can't be 98 degrees and 102 degrees at the exact same time.
Exactly. If a graph shows 2 different temperatures at the exact same millisecond, the data is flawed. It fails the vertical line test.
It's amazing how all of those concepts, slope, functions, scatter plots, rely entirely on the stage that Descartes and Fermat built.
Without the coordinate plane, none of that medical data can be visualized.
I do want to clarify one final thing from the sources before we wrap up.
Sure.
I saw a mention of polar coordinates. If this Cartesian XY grid is so universally powerful for graphing, why do polar coordinates even exist? Are they competing?
It's not a competition. It's really about choosing the right tool for the job. Polar coordinates are an alternative system.
Okay, how are they different?
Well, instead of moving horizontally and vertically across a grid, polar coordinates describe a point by its direct distance from the radius and its angle from a reference direction.
So instead of walking to a room and raising a bed, it's like standing in the center of the hospital, turning your body to face a specific angle, and walking straight in that direction.
Exactly. It's
Oh.
written as r, theta. Polar coordinates are incredible for anything involving circular motion or rotation, like radar sweeps, satellite orbits, or modeling magnetic fields.
But the TEAS and HESI exams stick strictly to Cartesian x and y.
They do, because nursing and allied health math heavily rely on linear relationships.
Right.
Ratios, proportions, and dosage per body weight calculations graph as straight lines. Cartesian coordinates are far superior for handling linear equations.
Well, we've covered a massive amount of ground today. Let's bring it all home.
Sounds good.
Based on our stack of sources, here are your 5 exam-style takeaways to lock in before test day. Takeaway 1. Room first, bed second. Always plot your horizontal x value before your vertical y value. Order matters.
Critical rule.
Takeaway 2. The 4 quadrants run counterclockwise. Upper right is quadrant I, where everything is positive. And then it goes 2, 3, and 4 in a circle. Takeaway 3. A point on an axis is in no quadrant. If there's a 0 in the coordinates, it's sitting on the fence. Takeaway 4. Negative coordinates are perfectly valid positions. They aren't mistakes, they just mean you moved left or down. And takeaway 5. Every graph is a translated equation. Don't treat your geometry and your algebra as separate topics to memorize. They are 2 languages saying the exact same thing.
If you can internalize the why behind those 5 points, you won't just memorize the material. You'll actually understand the logic behind the questions the exams throw at you.
Thank you for joining us on this deep dive. If you're heading into an exam soon, take a deep breath. You are going to do great.
You've got this.
But before you go, we want to leave you with one final thought to mull over. We spent all this time today mastering the flat, 2-dimensional Cartesian plane, right? Just an x and a y. But as future medical professionals, your patient's health isn't going to depend on just 2 variables. It'll depend on dozens of changing factors all happening at once.
Oh, absolutely.
Imagine what happens when we pull this flat grid out into a 3D space.
Wow.
Adding a z-axis for a 3rd variable, to track how a drug's dosage acts over time against a changing heart rate, or even a 4th or 5th dimension of data mapped by computers.
That's where technology is heading.
It makes you wonder, how might the vital sign monitors of the future visualize the total algebraic equation of a human life? Think about that next time you look at a blank grid. See you next time.